Hello and welcome to this video about strength of acids and bases. And in this video we're going to look at pH, the strength of acids and bases, and what buffers are. So a quick review, you all remember what an acid is. An acid, for our purposes here, is going to be a molecule that when it is dissolved in water, it's going to donate protons. A proton is just a hydrogen ion. It's a hydrogen nucleus only without the electron there. So when we talk about strengths of acid, a really strong acid is going to dissociate almost entirely. And here we are representing an acid by H, and then A would be whatever acid it is. It could be a chloride, a bromide ion here. It could be a polyatomic group of ions like a nitrate or a phosphate group. No matter what acid it is, when that is dissolved in water, some of those hydrogens are going to break off and dissociate into the hydrogen ion, and the acid part, maybe it's chloride, is dissociated into its respective chloride ion. And if an acid is really strong, like hydrochloric acid is a strong acid, it is going to nearly entirely dissociate into these two respective positive and negative ions. A weaker acid, on the other hand, this would be an example of a weaker acid, that the initial molecule, when it's dissolved in water, will have fewer molecules that are going to ionize or dissociate. And you can see that here, this is a very weak acid because most of that molecule doesn't ionize or dissociate into those respective ions. Most of it stays in that initial molecular form. Now the same is true for a base. A really strong base will have more molecules that ionize upon dissolving in water. Sodium hydroxide, for example, when we dissolve it in water, is going to form nearly entirely its respective ions. It's going to dissociate to a very, very large degree because it's a strong base. A weaker base will not have, they will have fewer molecules that ionize when they dissolve in water. An example of a weak base would be ammonia, NH3. Ammonia produces only a few ions in water, and most of the ammonia remains in the form of NH3. An important point, strength does not equal concentration. Very different ideas. Strong and weak strength, those refer to the degree to which an acid or base ionizes in solution. Remember, words that talk about concentration are words like dilute and concentrated. That refers to the amount of the acid or the base in the solution, but it has nothing to do with the degree to which that acid or that base ionizes. Now let's take a look at the pH scale. pH is a measure of the concentration of hydrogen ions in solution. And I'm not going to require that you know how to calculate this because I don't know if you've done logarithms, but literally this is the formula and the definition of pH, the negative log of the hydrogen ion concentrations. In essence, all you need to understand is that the pH goes down in numbers as the hydrogen ion concentration increases. So we can see that the pH scale goes from 0 to 14. 7 is right in the middle. So 7 is neutral. As we go down from here, we get more and more acidic. So the solution increases acidity. It increases the hydrogen ion concentrations, which makes sense, right? More acidic, there should be more hydrogen ions. As we get lower and lower on the pH scale. As we increase on the pH scale, as the number gets larger, the hydrogen ion concentration goes down. So at the end over here, we will have very little to no hydrogen ion concentration. And here are some representative items for these different pH values. You can see pure water would be neutral. As you go this way, you get more and more acidic items, and this way more and more basic items. So there are different ways that we can measure the pH of a solution. Let's look first at this idea of indicators. Indicators are simply chemical compounds that undergo color changes in the presence of hydrogen ions and hydroxide ions in solution. So here is just a chart that shows you there are many, many different indicators. Here are some common ones that show at what point or at what pH that indicator will change color. Now, let's say you are designing an experiment and you're starting out with maybe something that's really acidic, a solution, and you want to find different points when the pH changes in that solution. And you can see the ranges vary for all of these different indicators. If you wanted to, let's say, bromothiamyl blue, you wanted to really know when your solution was changing pH from just below a 3 to a 3, this would be a really nice indicator. It goes from yellow. If you add a little bit more base to it, you'll know exactly when you are at a pH of 3 and a little bit more, because it would change color at that point. Each of these, phenolphthalein is a very common indicator. Here, changing color at pH of 8. It's going to go from clear to pink, bright pink. Bromothiamyl blue is another one that will change color when it is at a pH of 7. Right here, when it's lower than that, it's yellow, and higher than that, it's blue. So just depending on what you want the indicator for, you can choose an indicator that will match the pH that you're wanting to look at. pH paper is simply paper that has an indicator added to it, and you can dip that pH paper into a solution and it will turn the color that that indicator will turn for that particular pH. So if you are using, I don't know, phenol red, and your pH paper is colored with phenol red, and you dip that into your really basic solution, that your indicator paper will turn bright pink. A pH meter is another device that can be very useful. Here's just a picture of one. They are operated by immersing electrodes in the test solution, and right here the electrodes are at the bottom here, and then you just simply read out the digital display. They're very convenient and precise, and you can get an exact pH measurement rather than reading a range of pHs that something may be. And the last thing we'll look at are buffers. A buffer is a chemical that will minimize the effect that an acid or a base has on pH. In essence, a buffer prevents large fluctuation in pH. So blood contains buffers. Here's just an example. This is some saltwater solution. It has no buffer. Blood, this is the same amount of 1 liter here, 1 liter salt solution, 1 liter blood, but it has a buffer in it. And why would blood contain a buffer? I want you to think about this while I just describe the situation. If we have 1 liter of salt solution and we add a milliliter of concentrated hydrochloric acid to this solution, the pH will go down. If we have a pH of 7.4 initially, it will go all the way down to a pH of 2. It becomes very, very acidic. Blood, on the other hand, if we take 1 liter of blood at a pH of 7.4, same starting pH, and we add 1 milliliter of concentrated hydrochloric acid to this blood, which, remember, has a buffer in it, the pH only drops a little bit to 7.2. So buffers prevent this large fluctuation. If an acid is added or a base is added, the overall pH will not vary tremendously. And why would that be important in blood? Did you come up with a good reason? Once you think about that, and for some advanced proficiency, you can tell me in class. Or maybe you would like some other ideas. Write a chemical equation showing the buffer, one of the buffers in blood, and how it acts to neutralize the addition of protons. Write a balanced equation for that and show how that chemically works. Or how does the pH of milk change as it spoils, and why? Or how about this? The value of pH is based on the logarithmic scale. So see if you can look at what that actually means. How many times more acidic is a solution with a pH of 2 than a solution with a pH of 3? Or maybe you have some other ideas. I look forward to seeing what you come up with, and we'll see you in class.